Okay, now let's see. So I did skip something. Yeah. So this is ID thing. I forgot to mention it. So I'm open software person and I like open software. If, however, you have a closed software hardware, and I won't be pointing in any fruits that may appear on that closed software thing, you won't be able to run it. So OS X won't allow you to actually register the networks. It won't allow you to run the script. So if you are a Mac user, sorry about that, but it's not going to work. Okay. So I want to speak about this. And can you tell me who actually played tic-tac-toe during the lecture when the part was boring? You can be brave enough. Yes? Okay, good. You deserved it. Okay. Is there a winning strategy in tic-tac-toe? Who say no? Come on. Yeah, that's tic-tac-toe. So who played it? All right. Once more time. Who played it? Oh, you got too many. Hey, did you play it? You played it. So let's see. Yeah. All right, so let's try once more. Okay. So let's see. How was it? Wait, once more. Okay. Okay, so we are looking over here. So you put in the center, then I'm going here. So okay, so you get this one. So the third one I'm giving this. No. No. There's a winning strategy. It's just I'm not prepared. Okay, we'll do it during the coffee break again. Okay, I should be better prepared. So I mean, in that over there, you should be able to read the winning strategy if you read closely enough. Okay, but the demonstration didn't work because I wasn't prepared. I haven't played it for a while. I mean, I should be sitting on the other sides for some times eventually. I will be more prepared. Sorry about that. All I'm claiming is that there is a winning strategy. And when I was a student, nobody could beat me. So obviously this is a finite game. So for every finite game, there is either a winning strategy for the first player or the strategy that ensures that the second player don't lose. That's the game theory fact. Very, very easy to prove. I want to play with a tic-tac-toe. So if you look at the property of the game, you need 5 moves at least in order to win the game. So that's because I start with X. There's the first move, and somebody put O, and then another X, another O, and another X. So in order to put 3 X's, I need 5 moves, and that's the minimal number of moves I need in order to win. after 9 moves, all the fields are used, so you cannot. There's a finite game, and you can generate the all possible endgame configurations, which are 958 of them. But that's a good observation. So when you look online, there's the division. Half of the resources say that there is a winning strategy. Half of the resources say that there is no winning strategy. I think it would be very good to write it down to actually have it resolved once and for all. Anyhow, I want to do a mapper on that thing, on this 958 endgame configurations. So by endgame, so let's say if X wins, then there's one more X than O's. If O wins, there's the same number of X and O's. And if there is a tie, then all the fields are used. So what I want to do, I want to take this field and convert it into a point in 9-dimensional space. And for this, what I'm doing is I put 1 instead of X, -1 instead of O, and 0 if the field is empty. So there's a good reason for that. We'll see it in a second. So for instance, the configuration like this, it gets 1 for X, 0, 0, 1 for X, -1 for O, 0, 1 for X, 0 and -1. Okay? So that's how we do it. We compute standard Euclidean distance, or maybe for simplicity, we just use the L1 distance. So we convert all those 958 endgame configurations. We get a point cloud in 9-dimensional space. We get the distance. That kind of makes sense. And there's one more thing I want to mention, which are the symmetries. So obviously, there's a diagonal symmetry. So this configuration, if I reflect it by a diagonal, I get this. If I reflect this via diagonal, I get that. If I reflect that via diagonal, I get this. I can reflect it by this axis to get this. I can reflect it by that axis to get that. So that's obvious observation. A nice mathematical way to say it is that there's a dihedral symmetry group acting on the square, and we can take a configuration which is winning or losing, or a tie configuration, run it through the dihedral group, then we'll get the same type of configuration, just different, and eventually we can come back to the same configuration if we run it large enough. So over here we have a quite nice combinatorial example of the data set, which we can convert into a point cloud in 9-dimensional space, but in addition it contains symmetries. That's not something very untypical. I mean, in many physical data sets you do have symmetries. By the way, on the coffee break we continue. All right? I won't let you go that easily. So we have the symmetries, and we would like our TDA invariants, in this case mapper, ball mapper graphs, to respect those symmetries. So if we just run mapper, or in this case ball mapper, for epsilon equals 2.5, we get an image like this. So I think, as far as I remember, red was the win configuration for the first player, that was the lose configuration, and we got, I think, 16 ties. So already we can see something about the game. So this is the coloration. So all this cluster, this subgraph contains only winning, this only losing, and the separated points are the ties. Already we see something of the combinatorics of the game in the ball mapper. What I want to do right now is to take the symmetries into account. There is some obvious dihedral symmetry in our data. I want the ball mapper to preserve it, and I can do it using the appropriate adaptation. So essentially, in the landmark selection procedure, when I'm selecting a new landmark, I'm actually also adding all the elements of the orbit of this landmark. Happy to discuss more, but there is a way. Let me actually press play. So if we do it, we got those, have a better picture. So what you can do, you can scan the QR code and actually have the interactive visualization of those things, but we have the lose and win and the tie configurations. And now, if you scan it, I can take a better view. Sorry about the background, it's still not. Okay. So that's the winning cluster. And if the points, they have the same color, it means that they are in the same orbit. So if I take, all the configuration of the here and take an element of the dihedral group, it will bring me over here, then over there, and then perhaps back. So this orbit has a length 4. So we see the symmetric structure. We see how the symmetry of the game is reflected in the structure. Likewise for the losing configuration. So again, as I mentioned, we cannot jump between win, lose, or tie because the dihedral group preserves the outcome of the game. So we have 3 X's in the row, whatever the row is. After whatever action of the dihedral group, we'll still have 3 X's in the row. The same for O's. And if we don't have 3 X's, we won't have 3 X's after the application of dihedral group. So it actually preserves. If we start to play with the ball mapper for different resolutions, so for epsilon equals 2, we get this very nice subdivision into win, lose, and ties. Epsilon equals 3, win and lose actually get merged together, ties stay separated, and they are still separated at epsilon equals 4, at epsilon equals 5, they get merged together. So that's an interesting observation, and we can actually go back to the data and make some conclusions. So we hope to write it up as a kind of, fun thing you can present to high school kids if you want to show them some mathematics and high dimensions and maybe data analysis tools. So let me briefly walk you through. So this is still very much work in progress, or the work that we are starting, but I'm crazy enough to put it right now on the lecture. So let's see how it goes. So what do I mean by a 2 sequence? So if I have an endgame configuration and it's either win or lose, there is a 2 sequence between any pair of win or lose configurations. So if I take 2 win configurations, I can actually produce a sequence of win configurations such that every 2 constitutive ones will be of a distance 2. The same for the lose configurations, and will connect any 2 win configurations. And the idea is essentially by an algorithm. So if we start from this minimal configuration and we want to move from the horizontal, or from the vertical minimal configuration, we want to move to the diagonal. We are doing this by introducing a pair of X and O's to the empty places. The cost is, 1 is 1. This is 1 and used to be 0, so the cost is 1. This used to be 0 and is minus 1. The cost is 1 again. So the distance is 2. Likewise, the distance is 2 over here. And then we are removing pairs. Again, distance is 2. And if you actually think a little bit about this, that you can actually find a simple algorithm. It will produce such a sequence between any 2 pairs of the configurations. So what does it mean? If we come back to the picture over here, it clearly explains why wins and ties are connected for epsilon equals 2. You got the sequence. Ties are a bit farther. So there is, where are ties? So in order to actually move between win and lose configuration, you need to jump at least by 3. The reason is you need to remove. So when you have a winning X configuration, there's one more X than O, so you need to remove the X and you need to add one O, and that's a cost of 3 already. so you can prove it combinatorically. And it kind of so doing data analysis of this type justify you to think a bit deeper about the types of games you are playing, and we have some things to settle on the break. So that's the type of recreational mathematics you can do using those tools. In Houston, we have a problem with a connection. So I'll be moving to the dynamical system in a second. And also trying to use the idea of mapper, more mapper, and tie it to some standard topics in the theory of dynamical systems. All right, we are back. Okay. So before we go to the dynamical system, I want to speak about the time series. And I actually spoke a little bit about it already. And if you remember the Wesley Crusher example of copper mine industry, they have a time series of vibrations of some mining machine, and and the time series we needed to convert into a point cloud. We kind of swap it under the rug and nobody asked, but actually we need to think how to convert time series into point clouds, because they're pretty common means of representing data. So there are many data sets in the form of the time series. There are a number of ways you can do. So if you think about the standard time series, it does have some topology by itself, but the topology is pretty boring, because on a given level set, you can look at the upper level sets and you can see how those evolves as you move up and down the threshold value. This way, you can get the information about the evolution of the connected components. But with this, we are not going to get any more interesting topology than just the connected components. But there's another way. And what I want to speak about is exactly this mechanism of the time delay embedding, which is something very heavily used in theory of dynamical system, and it's actually very well justified. And I think it's something which is very much underexplored, and something that has a huge potential for equation-free modeling, if you know what I mean. So let's imagine that we have a time series which is sampled at some discrete points. I will have, because there is a sliding window, there's a window over here. So the window size, the window is big enough to actually contain 6 points, 6 constitutive points. So I'm looking at the value of the points which are in the window, and I am actually concatenating them in the vector of 6 elements. So for that vector of the value of the functions, the y value of this function, represent this particular placement of the window. So that's a window, and because it's called a sliding window, now I'm going to slide the window, and I got another point, a little bit close by, but we don't have x1 anymore, and we have x7 instead, and then I'm sliding it again. And this way, I'm kind of encoding the shape of my function in a form of, in this case, 6-dimensional collection of points, 6-dimensional point cloud. This point cloud may have some interesting properties, and this is what we are going to speak about. So over here, I just took the constitutive points. You don't need to do it. You can just take, necessary. You can skip some of the points and have a sliding window of, for instance, this form. Does or does not. It may have some meaning. So we'll play with this in a second. So the kind of intuition behind that is that the sliding window. So this point kind of encodes the local shape of the function at the position of the window. So that's the way I'm thinking about it. I'm not saying that this is the way to think about it, but this is the way I'm thinking about it. What I promise you is somewhat a connection between this time delay embedding and the dynamics. So let's think about it. let's imagine that you are observing a state of the atmosphere by measuring a temperature in Mérida every 5 minutes. Got a time series, and you want to understand the property of the dynamics, which is the weather in the planet Earth. That looks, I mean, it clearly, the temperature you are getting right now over here is a function of the global state of the atmosphere in the whole planet. We are having some very, very simple observable. The point I'm trying to make is when you are observing it long enough, you can do some reconstruction of the dynamics, which will somehow correspond to the initial dynamics. If you think about it, it looks like I'm saying something which is absolutely impossible because it's so far-reaching that, I mean, that clearly cannot happen. Well, it does. So we look at Takens theorem, Lorentz Takens, 1999 and 1991. We have a chaotic dynamical system, weather is chaotic. We have a generic observation function. By generic, he means really a dense subset. The generic observation functions, they are the dense subsets of all possible observation functions. So for instance, I can measure temperature, I can measure the pressure, I can measure something else. And then he is claiming that if I have such observation function, infinite one, I can reconstruct the dynamics, the state space, and the dynamics using the machinery of this time delay embedding. Of course, you know, the devil is hidden in details. You really need the infinite time of some sort, but it's still something very, very, very strong. Doesn't give you the parameter of the time delay embedding, so you don't know if you are having this strategy or maybe that strategy, what's the window size, how many constitutive points, etc., etc. That you do not know. But you know, there's this Takens theorem. So I promise you the weather. So back in the 60s, Edward Lorenz actually was playing with an equation of fluid dynamics, discretized them in quite kind of brutal way, and he got a system of three equations. I'll actually show them in the notebook in a second. And then, I mean, that was this funny story. When so I think that there are two stories when people discover something by coincidence. The first is, I think it was Fleming who discovered penicillin. And the reason he discovered penicillin is because he had a dirty table. And they were growing some bacteria, but, you know, I guess, okay, I'm probably exaggerating. He left a sandwich. And then there was this white mushroom on the sandwich you get if you leave it for too long. And then he realized that, you know, the bacteria are not invading the mushroom. And so therefore, there need to be something in the mushroom that kills the bacteria. And, you know, 2 years later, he got the penicillin out of it. And another one was Lorenz, who was running some computation on this system. So there's a system of three differential equations, ordinary differential equations. But at some point, you know, there was a power cut or something. So he came to work after, you know, the computer was supposed to compute for many weeks. And, you know, there was a power cut, the computer restarted. That's a bad day. He was somewhat lucky because he stored intermediate results a few days before. So he said, okay, well, I'm not wasting my whole month of the computer power, just those few days. So I'm just, you know, running those from the initial condition and we'll continue. This is what he did. He continued. But you know, he was looking at the intermediate results and he realized that what he sees is not what he saw a few days ago. What the heck happened? Well, after many research, he realized that he stored the results up to, like, I'm making up the number, 4 digits of precision. But internally, the computations were done on the 8 digits of precision. He lost the precision, and because of the loss of the precision, very quickly, he got very different solution. So this is what we know right now, and what he actually described in his paper as a sensitive dependence on the initial condition. So there is a continuous dependence, but the sensitive dependence is, you know, you can start very close. You have two initial conditions which are very close to each other, but if you run the dynamics, they get very far away. very quickly. You typically may know it as a butterfly effect, right? So there's a butterfly in Amazon jungle, and we have in 2 weeks we have a hurricane somewhere. That's this how sensitive the dependence may be, and that's the attractor he was actually looking at during this, and he discovered chaos this way. For many years, he was actually trying to push it through community of pure mathematicians, and they realized no, this is not the case. It's only because you are not working with ideal mathematics. There is nothing like this in reality, in real mathematics. And only Steve Smale at some point, actually, by showing the Smale's horseshoe, he actually made a point that that's a real thing. So it's also an example of nice numerical discovery that needed a lot of time and perseverance in order to be accepted in the mathematical community. So that's our unknown dynamics. Well, what type of observation functions I may have? So once we have this trajectory, I may record, for instance, just the x-coordinate. And I'm getting a time series like this. The y-coordinate, or maybe the z-coordinate. And what I'm claiming, or what Florence Takens is telling us, is that if I do time delay embedding on that thing, if the thing is generic, I should be able to reconstruct the attractor. And so that's the reconstruction based on the x-coordinate and some luck. You see, it's not the same attractor, right? But there is some. I mean, we can imagine that there is a diffeomorphism, and indeed there is. This is y. This is x. This is y. This is z coordinate. So it's clearly there is something wrong with z. There's a part of a homework. What's wrong with z coordinates? So z is not generic, clearly. But before we actually get to the example, I mean, what if we have what I'm saying is that if we have sufficiently long observable from the generic function, and we do this procedure, we should be able to recover the dynamics without trying to fit, without trying to guess, okay, which system of equations with which parameter it is. Purely data driven. And I really like it because it really. So that's what Takens theorem is telling you. So if you do the time delay embedding, you are getting a reconstruction of the phase space and the dynamics, which is diffeomorphic and topologically conjugate to the initial dynamics, which you do not know. Right. So you have a surrogate model, as you wish, that tells you that has the same dynamic with any measurable sense in mathematics that the original one, which we do not know. Who have a question? You have a question.
If there is a way to define the bed size of it?
That's a fantastic question. So there are a number of techniques which are heuristics. One of them is called false nearest neighbor. You can actually also look at my recent paper with two of my postdocs, Justyna and Michał. Recently appeared in one of the SciAm journal. It's a beast. It's like 60 pages paper when we are looking at various possible techniques to do it. Yes, there are ways. If you have enough data, you should be able. So we have a theorem that if you have enough data, you will get the right parameters in terms of the size of the window and the luck. And we have like 10 different examples in which we are illustrating how it works. So yes, under the caveat that you have enough data. Stationary time series. Okay, so in whatever I'm saying, the time series is fixed. So you don't have a control over the time series. It's just you. What you have a control is the size of the window. So how many points? Maybe 3. Maybe I should take another one over here, and the luck, which is the the spacing between those. Those are the parameters. So you have a God given. You are coming back from the mountains. You are carrying the time series. God given. So you're not touching it. You can just interpret it. And the thing you can control is the interpretation. Make sense? Okay. Any further questions?
Yeah.
Tell me.
So I understand that here that we get where we sample the function the time and we have the video and
Okay. So I mean, you have a discrete dynamical system, and the time I you have this point, and the time I plus 1 you have this point, and the time I plus 2 you have that point. Make sense? So that's for discrete. For a continuous, you can figure out what to put in the middle. Okay. Does that answer your question? Kind of. Okay. If you have more specific one, tell me. I want to find what? Okay. So we have discrete dynamical system, right? I just want to know what's F.
I don't actually. I think you want to know where equals 0. I feel like that. Well, we just said it's not there. We don't know that. We only know when cap to this output, right? So like for the lower end of factor, we know it's a 2 point
Okay. Okay. So let me do the demonstration, but f prime equals 0 only in the critical points, right? So in Lorentz you have a critical solution. I'm recovering much more than that. This is what I'm saying. Okay, let's take a look. All right. So where am I? Let me just put it into the context. There is a practical time delay embedding demonstration. Yeah, so let's do this. So I'm starting with something easy, which is again a cycle. So I have a dynamics in which it's okay. So I haven't plotted that, but where is it? So if you look at the trajectory that is moving on a cycle, and you're observing one of the coordinate, so one of them will be a sine and another will be a cosine, right? That's reverse way of thinking about standard parametrization. So what I did over here is to put as my function a sine, and what I'm trying to do, let me no spoiler alert. So let's do it again. Say again. Yeah. But I with one hand it's problematic if I'm keeping this. Okay, whatever. So we are actually doing what we are doing. We are taking a sample of a sine with step 0.1. We are taking 10,000 samples, and that's a 2D reconstruction. Let me do a 3D reconstruction for you as well. So if the dynamic is circular periodic motion, we kind of get it. It's not extremely circular. So you can, for instance, take a look at Jose Perea and John Harrer paper, which is called Swipers. And they say that, you should probably look at the larger log. So over here, log is 10. Let's see what happens if I put log 100. See that thing is actually getting more circular. Maybe 100 is not good enough. Maybe 200. So if I do this, So I'm getting a reconstruction from a simple periodic motion right now. Okay, that's not exactly what I promised to you. But again, if you actually color the points by, the number in the sequence, you could really see the dynamics. You can see the point moving around. Let's take a look at Lorentz. So what I have below is, so those are this is the Lorentz equation with a pretty standard selection of the parameters. So if I integrate it for 20,000 iterations, starting from this initial condition 1, 1, 1 with this step dx equals 0.01, this is the attractor I'm getting. Let's take a look at the x, y, and z coordinate. And once again, those are the reconstruction that you've seen so far. But again, if I'm looking at the prefix and I'm tracking the trajectory in the original attractor, and Greg, that goes to your question, and in the reconstruction, there is a diffeomorphic correspondence between them. So what I'm saying is that, to my understanding, Takens is saying much more than just about the the critical points of the dynamics. And I think that that's something, I first heard about it more than 10 years ago, and I'm still amazed about this theorem. So it's blowing my mind, honestly. Any questions? I mean, play with it, play with the parameters, and I think that there's something very nice to explore, and we are kind of also exploring it with within my center. So okay, so if we have a reconstruction up to the diffeomorphism, then we were also reconstructing the invariant sets. I want to give you a simple illustration. So one possible, one of the cool invariant sets are periodic orbits, and time series and the periodicity of the time series and the existence of the periodic orbits, they come kind of hand to hand. This is what is happening over here. And if you think about it, so once we have a periodic time series periodic function, then if I have a window positioned over here and the window shifted by a period, I'm roughly looking at the same shape of the function, right? And I'm shifting in between, I don't see the same shape of the function on the way. Very much like with the lucky cat. So that's why if I take a time delay embedding of something periodic, I shift the window, I'm starting to see a circular time delay embedding. So circular dynamics happening over here. So periodic time series corresponds to periodic orbits, and we can reconstruct those periodic orbits. Starting from a sign, we can get this nice periodic orbit. And of course, once we have a periodic orbit, we forget about the order of points. Then the whole business of TDA is coming into the play. So for instance, you can reconstruct this phase space of some dynamics from one time series. You can reconstruct the phase space of the dynamics from another time series and compare the phase spaces. So you forget about the dynamics. I have this additional information, but I may choose not to use it. And well, if the phase spaces, if we see that the phase spaces have radically different topology, then we know that the dynamic cannot be the same. So we know that the underlying dynamic is different. That's more or less what we did with this crusher example, back on the topological test, on the topo tests. But nothing prevents me from, if we have a periodic orbit, that's ideal, Platonic ideal thing. We only have a sample. Nothing prevents me from doing mapper on it, or a ball mapper. Once I do a ball mapper, I immediately introduce the symbolic dynamics. So if I name every ball with a certain symbol, then I can bring the information about the order of points back to the business. And then, if I have a trajectory moving around, I can track the symbols that are encountered. So if I'm coming over here, I see a lot of points labeled A, and a lot of points labeled D, then a lot of points labeled B, and then a lot of points labeled C. And the story continues. So what I'm saying is, in this case, I can actually look at the flow between different vertices of, in this case, ball mapper graph. That if I discover a reasonable direction of flow, I can actually direct my edges according to the flow. Yes. Oh, okay. So the orientation is, if I look, so if I'm moving around this orbit clockwise. That's right. Exactly. Orientation by precisely. Okay. Any further questions? So I have this dynamic graph. I have a symbolic dynamics attached to this, and well, I have a tool to, starting from maybe noisy time series, lift it to higher dimensions and try to look for periodic orbits by looking at these periodic sequences in the ball mapper and try to detect periodicity. So that's a Melbourne temperature in 9 constitutive years. And we were able to recover information, and the year has roughly 356 days, 65 days. I mean, that's not a big thing, but we are able to get the period quite accurately from reasonable noisy data. So temperature data from Melbourne, in this case. Well, there is a variation, of course, because not every year is the same, but we are pretty close. We compare it to say standard spectral-based methods. We are similar in accuracy, although we are using something conceptually simple. So time delay reconstruction with tokens and this periodicity detection on the ball mapper. But what I'm saying is that thing has a potential, for which the spectral methods may actually fail to work. So imagine that you have a machine that is working on a different speeds, right? Maybe moving slowly, then very fast, and then kind of intermediate speed, and slowly again. When you are looking at the speed, you get a plot like this. So that's the dynamic plot. If you actually trace what is happening in the symbolic dynamics, first you are moving on one of those cycles, then maybe you are moving on the other, and then you are moving on the other. So this is not what is visualized on those graphs, but you actually see how you first of all see that there is a composition of free periodic motions, but in addition to that, you see a transition times between them, again directly from time delay embedding. And I'm not claiming that this is something you cannot do with the spectral methods if you actually start to focus on the sub-windows, but it kind of comes naturally in topology with those symbolic dynamics. And if you want to mapper plot, then you will see that first of all you are moving around one loop, and then you are moving in the phase space to another loop, and then you are moving in the phase space to another loop, which is no transition between here, 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 and there. So that's something which very nicely came across using those topological tools. So there's a continuous change of period. Imagine that you are sitting in your car, there's a red light, and then becomes green. So you are starting to accelerate. And you have a sensor on your wheel. So first you are moving slowly, but then your wheel is turning faster and faster, and you are increasing the speed. If you do, well, there is no well-defined period, but if you do a time delay embedding of it, so there's a time delay embedding into 100-dimensional space, and I left a note that I should show you the that thing. So you really see, so it doesn't have labels. You really see that this is a cylinder. So we are starting over here, and the trajectory is wrapping along a cylinder, in this case in this 100-dimensional space. So I hope you are able to see that actually we have this cylindrical behavior over here. Damping effect. So imagine that you are on the swing. First you are moving quickly, but then there's a friction, so you are slowing down. You get a time series like this, perhaps that's a better picture. So first you have a high amplitude, but then you are wrapping on a smaller amplitude. Looking at the symbolic dynamics, you also get this information. I won't be going into the details, but kind of matching together time delay embeddings with symbolic dynamics and mapper type algorithms give you some new possible approach of analyzing stuff. Yeah, this is the time series. So I actually I sampled it. You can actually see that there's a discrete sample. Tell me, on the window size.
I assume if you make it too thin or too broad, you don't know to take the dynamic. You need to kind of
Okay. So if you make it too small, you won't be able to detect the dynamics. Taken's theorem says, so you're looking at the Hausdorff dimension of the attractor of your dynamical system, and Taken say that you need to be 2 times this dimension plus 1, which is very much related to what Greg speak yesterday. So the Whitehead's embedding theorem. There are some results that if you are okay to make mistakes on the sets of measure 0, you can reconstruct to the same dimension as the dimension of the attractor. If you reconstruct below, this is not going to work. So but if you are longer, that's okay. If you are too short, that's bad. Okay. Any further questions? So, okay, guys, I was torturing you with the violin phase, right? So we can do this reconstruction. So yeah, I had another one over here. It's slowly changing. Yeah. Then let me do it again. Yeah, I need to find my zoom thing. I push it somewhere to the side. And that's actually a very nice experiment. Oh, there it is. I think it was over here. Okay, I think that's enough. Okay. So we have this reconstruction. The period was more or less the period of the motif, but then okay. So this was a very nice experiment done, very recently, but by Davide, my PhD student. So first of all, we tried. To just take a YouTube recording. But this is what happens when theory meets practice. We realize that signal to noise ratio is too big. We are not able to see anything. Therefore, we actually go to the nodes and generate the MIDI file, which was exactly what you heard over there. We didn't have a problem with noise over there. We are able to do this reconstruction. So the phase space, and you can actually play with it. It has a very bizarre shape. So this is where the dynamics is happening. So imagine that you have some, a rubber or something, and then I press my fingers over here once and over there twice. So that's the shape of the reconstructed phase space. And actually, so again, we didn't write it up yet, but you can argue that when there is a shift, when the players are going out of synchrony, you are kind of shifting continuously on that space, and then when they are coming back to synchrony, you are coming back. So we have a kind of a periodic orbit with a drift, and then it's coming back. when they are getting back to the synchrony. So again, that's one of the examples where you can use the mechanism of time delay embedding combined with mapper, combined with symbolic dynamics in order to analyze music. And you know, if you like the motif, that's Steve Reich, violin phase. It's composed roughly 1960, 1950. Yes. It's a good question. We haven't done that far. It should be a projective space. I agree. Yeah. I mean, we have the point cloud. It's just a matter of running code. Yes, we haven't done that yet because we are focusing on the dynamic. That's a very good point. Thank you. No? All right. Scream next time because I may not keep the eye contact constantly with everybody. So if you have questions, please speak up. All right. So we have the Steve Reich thing. If you want to play with it, is on the Davide's GitHub. So the drag of period, the embedding, symbolic dynamics. I think, you know, there's a lot of stuff that we can do over there with this. Okay, guys. So we have 12 minutes, and then we have another hour, right? Yeah. All right. So there is an option. I can speak about graph theory, not theory. I can speak about algorithmic approach to discrete Morse theory, or we can go to the dynamical system. Morse theory. Morse theory. Not theory, Morse theory. Okay. So what I won't be doing this. So you know, inspiration is the same as Jesus Gonzalez, but I want to give it algorithmically, and I want to refer back to the algorithm to compute homology and persistent homology and how those two are related. How we can use one to compute the other. And actually the inspiration may go both ways. So let's try to make a connection. You know, in mathematics, as in everyday life, everything is kind of interconnected. So let's take a look at the Raoul's-Bott secret weapon. Okay. You had it already, but let me very briefly recall. So we have nice regular CW complex. You may think about simplicial complex K. And we have a function which is constant on every simplex. And then those are the two terrible conditions. Every time I'm looking at them, I feel very, very bad and sorry for myself and even more sorry for you. But let's try to do it together. So if I'm a simplex, and I'm looking at the simplices in my boundary. So I want to compare the value of the function f for me and the value of the function on the simplices in my boundary. And the conclusion is that my value should be greater than in the boundary. There may be one exception, at most one exception, right? There may be one element in my boundary which has higher value of the function f, but there cannot be two. There can be 0, 1, but cannot be 2. So that's the condition 3.1. Condition 3.2 is if I'm looking at all the simplices that I am boundary of, so my co-boundary, they should be higher than me with respect to the function value. Again, one exception is possible. So this is what that thing is saying. Simplex is critical if we don't have exceptions. And you can prove some interesting things. Does it make sense? Who says yes? Say yes. Okay. Tell me. No, so you're supposed to ask questions. You answer the question. You don't get the chocolate for answering the question. So one of them is a discrete Morse function. Okay, we discussed about democracy, right? That's the democratic theorem proven. Yeah, the left. No, right. Okay, no. Who votes for left? Who thinks this is a discrete Morse function? Or by my left, who thinks this is discrete Morse function? Hands up. Who thinks this is discrete Morse function? Okay, let's say that there is a majority. I am too lazy to count. I'm topologist. I have not become a topologist in order to count. Come on. Okay, let's take a look. So once again, remember, if I'm a simplex, in my boundary, they have to be lower, one exception possible. In my co-boundary, they have to be higher, one exception possible. So let's do one by one. That's a one-dimensional simplex. They're in the boundary. They're higher. That's bad, two exceptions. So we already know that that's not the case. If you look at number 5, in my boundary, in boundary of this vertex with value 5, they are lower. Again, more than one exception. Clearly not. So, to be on the same page, let's look at your right-hand side. That thing. So if I'm on the vertex 0, this is higher, no exception, perfect. This vertex, this is higher, this is lower, one exception, we are allowed to have one. Likewise over here, this is lower, this is higher, one exception, we are okay. That edge, this is lower, this is higher, one exception. Lower, higher, one exception. Lower, lower, no exceptions. That's the discrete Morse theorem. Discrete Morse function. Okay. So why we call it discrete Morse theory? Because there's this continuous Morse theory going back to Raoul Bott, and it has a lot in common. Say, and what does it have in common? I've kind of highlighted over here, but I won't be going through details because you already seem too tired. When there are exceptions, so exceptional cells came in pair, face and the copies. I can put an arrow between them. This is what Jesus done yesterday. This way I'm getting a gradient flow. And, that's a much nicer way of encoding discrete Morse function instead of those numbers. So, in practice, we almost always just put the gradient, making sure that the gradient is scalar free, so we don't have a closed cycle over there. So every simplex can be a tail or a head or none of an arrow. Critical cells of the Morse functions are those which are not paired. So they are neither tail nor a head of a pairing. So essentially what I'm saying is, if I have this very simple one-dimensional simplicial complex, I can assign arrows. I cannot break two rules. I cannot assign one simplex to two arrows in some way, and I cannot create a loop. I cannot create a closed loop. So now I can happily start assigning them. And I cannot assign this one anymore because it would create a closed loop. It wouldn't be a gradient field. I cannot pair it this way because then I would be pairing this vertex to two different arrows. So there is nothing more I can do. I just need to leave them as critical. In this way, we are getting a representation of the initial complex with one critical vertex, one critical edge. If you compute the Morse boundary, and again, this is what Jesus was explaining formally yesterday, I mean, the boundary of this edge, at one side we have, the vertex over here, but if we follow the gradient path, we get it once more with an opposite orientation. And, this orientation coming from this side, this orientation cancels out with the other orientation. So I'm getting a complex. I can think about it as a chain complex with a null boundary. So something that essentially gives me homology straight away. Okay? And that's a cool stuff because, we computed a homology of something maybe easy, but if we just wanted to do, standard thing with a boundary matrix reduction, that would require some work. And over here, we just, placed some arrows and it worked out. The question is how far away we can carry this analogy. So I'll mention again what already was said about discrete Morse complexes. So discrete Morse complex, it has cells, which are critical cells of my flows. And the flow gives you the way of assigning the boundary. So what you need to do if you have two critical cells, let me call one of them A and another B, and there are a number of pairings in between them. over the two coefficients, what I need to do is to count the number of paths, which, by the way, is not a trivial problem. How many paths are there between A and B? Well, you need to count number of different paths. So they may have some intersection, but if they are different at some point, then the paths are different. How many paths do you see between A and B? 4. So let's see, I can go, yeah, democracy wins. I can go right here, this is path number 1. I can go here and down, this is path number 2. I can go down and here, this is path number 3, and I can take the lower path, this is path number 5. Why? Okay, so you are saying that I should put A over here, right? And that's my B. Yeah, I mean, that's just an illustration. I agree. Right. So formally you're right, but that's not the encoding of a simplicial complex. This is just, so some encoding of the paths. And what I meant to show over there is that it's easy to define, but the number of paths, if you start drawing such a diamonds, then the number of paths, if I have n diamonds over here, then the number of possible paths will be, okay, 8 over here. And if this is n in general, 2 to the n. And calculating it is maybe pretty intensive. So that's not an easy problem, even though we are dealing with a directed acyclic graph. There is also some algorithmic work that needs to be done over here. And do I meant to say anything else? Yeah. So the Morse complex and the initial complex, there is a homotopy equivalence. And what I want to do after the break is to say, okay, forget about homotopy equivalence. Let's do a Morse complex. And then let's do another Morse complex of the Morse complex, and the Morse complex of the Morse complex of the Morse complex, and the Morse complex of the Morse complex of the Morse complex of the Morse complex. Let's see where it gets us. So what I'm assuming is that when I'm doing Morse complex of the Morse complex, I'm making at least one pairing. So when I'm making at least one pairing and I'm starting with a finite complex of some sort, the number of cells is going down. Eventually, that thing needs to stabilize. So eventually, I should be able not to do any pairings. And what this object will be then? Well, you need to wait until the break. Thank you very much for now.